Does my screen appear to you?
Yes, sir.
Yes, sir.
Okay, thank you. Remember last time we were discussing, I was discussing processor design, and then Professor RSC took over and you studied in the meantime a little bit of operating system, memory hierarchy, cache, main memory, virtual memory, and something concerning the interrupt also, right? So today we are almost at the end of the course and only 2 more weeks to go, and I'm going to talk about the last topic, and one of the most important topics in computer organized architecture, and this is pipelining. So before I start, let me have a quick recap from where I had left. Do you recall this diagram?
Yes, sir.
I think you have already, in your lab, you have already done some experiments with it. So what is it?
Data path of a single cycle processor.
Right, data path design of a single site processor, or you might say that this is the overall organization of a single cycle processor. And as you can see, it has different components. So can you recall that what kind of instructions can be executed by this primitive processor? What are the instructions that are implemented here?
R type and load store instruction.
Load store, R type, and
Branch.
Branch and jump. Isn't so? So you can see here, this is the portion where the jump instruction has been taken care of to find out the target address, and this is the logic that takes care of the branch address whenever the branch is taken, and you have all these AND gates and so on, all kinds of data path and so on. Okay, this is the primitive processor or data path, you can say, for implementing these basic instructions: load, store, add, subtract, and or. And you remember that this ALU also realizes SLT, shift set less than instruction, branch echo, and jump. So now please tell me that, so you have different hardware resources, as you can see here. You have memory here, processor, program counter here, an adder here, then control logic is here, register file is here, ALU, and this is the memory. You have instruction memory and data memory, and different muxes, and little bit of logic, some shifter, sign extender. So remember that in MIPS instruction, what are the various steps or what various cycles? Small
The
cycles.
instruction fetch and decode, register, reading, ALU, and write back.
Memory. ALU, after ALU.
Memory access and then write back.
Write back. And instruction decode and register read, that can be done in one phase. Remember? So if we look into
Yes.
this hardware layout, we can see that this is the portion which is responsible for instruction fetch, because program counter supplies the address of the current instruction to be executed. The instruction is read from the memory, and at the same time PC is updated and so on. So this portion of the hardware is responsible for instruction fetch. And then you have to read the instruction, and this control logic decodes that meaning of that instruction. And once you decode the instruction, the appropriate logic is set on this output control lines. And these control lines actually, they enable different multiplexers so that the appropriate data path is enabled. So this portion of the hardware is responsible for instruction decode, and register read. And then you have this execute. And the execute fetch, we also do address calculation if it is a branch instruction or a load instruction or a store instruction. Isn't so? If it is R type instruction, you execute it like addition, subtraction, or some logical operation. But if it is load, store, or branch, and then you compute the address here, right? So that in the next step, either you fix this target address or you access the memory. So this is the portion of the hardware which takes care of the execute and address calculation phase. Then you have memory access. You have data memory. You access that. And finally, write back the information back to the register file here. So this is the 5-stage, the 5 basic steps in every MIPS instruction. Instruction fetch, decode, register, read, execute, memory, and write back. Well, so as we have said that this is a single cycle processor design. So what are the design characteristics and consequences? What does it mean that it's single cycle? We have just talked about that there are 5 stages in the MIPS instruction fetch, decode, and etc. and so on. So when I say that it's a single cycle processor, what does it mean?
Sir, every instruction has to be completed in one cycle.
Yes, that means all the 5 stages that we have discussed, instruction fetch, decode, and etc. Everything has to be completed in one clock cycle. Now let me ask you a question here. Suppose I have a shift instruction. You know that in shift instruction you can shift the content of a register by number of bits. How do you implement it? I mean, shifting by say 5 bits or shifting by say 30 bits.
So barrel shifter.
Barrel shifter you can do. It's a combinatorial barrel shifter. Regardless of the amount of shift, you can implement it in one clock cycle. Otherwise, you have to do sequentially. Okay, good. And in the meantime, you have also studied about memory hierarchy. And you have noticed that, well, if you start from the CPU side, and then on the CPU I have the register, then I have different levels of cache, L1, L2, and so on, followed by main memory, hard disk, and network, and cloud, and so on. And CPU is somewhere sitting here. Okay, and you already know that what are the typical sizes of this. As you go down, what happens?
Gets slower.
And so that means as you go up, its speed is you have a higher speed. Faster resources, and obviously, it will be higher cost. And if you go down, that increases the storage capacity. Okay, so now you have studied these complications of this memory hierarchy, how the memory is accessed, how the cache is accessed, and so on. So what is the purpose of having this memory hierarchy? What is the net objective of using a memory hierarchy like this? Why do I use this?
You don't need all the data at once.
Well, your ultimate objective is to speed up the system, isn't so? So I want my CPI to be low. Amount of clock cycle, number of clock cycle per instructions. Yeah, so use of hierarchy that speeds up the memory access time. Now, since you have a better understanding of the memory hierarchy, now let us look into this picture once again. We have discussed it in previous classes, but now let us look into this picture since you are now knowledgeable about memory hierarchy. Okay, so you have cache memory, main memory, secondary memory, tertiary memory, and so on. Okay, now you please tell me, how do I access a hard disk? What are the basic mechanism of accessing a hard disk, or what are the basic steps which you need to follow? Suppose I supply an address, how do I access my file from the hard disk? What kind of procedure is involved?
So we make a system call, and then the kernel will make wait for the interrupt, and that interrupt will be handled by the device driver, which will give another interrupt to let the kernel know that we have got the file back.
Yes, and then in the hard disk, you have to look into the appropriate cylinder, right?
We're seeking.
And then the read head should go there and read the data and do the reverse process again, isn't so? So you realize that, first of all, the user memory hierarchy reduces the transaction time across CPU memory interface because of the memory hierarchy. And this uses the principle of spatial locality and temporal locality. And you already have this understanding of this logical address versus physical address, right? A logical address is supplied by the program counter, and then it is mapped into the physical address. Okay. And as you see, as we have just discussed, that hard disk is essentially, basically a very slow process. On the other hand, on the processor side, CPU and this logic, those are faster devices. So there is an inherent speed mismatch, right? So suppose CPU is asking something from memory and the memory access is slow. So just like the stories of this hare and tortoise, although the CPU side is faster, this hare has to go to sleep for some reason, isn't so? Okay, so memory transaction is inherently slow to logic. Now since we now have a complete view of the system, let us now revisit this problem. What are the consequences of having the single cycle processor design? We have just discussed that everything we have to finish in one clock cycle, right? So instruction fetch, decode, and then the register read and decode. Instruction fetch, then register read, decode, execute, memory, and write back. Everything has to be done in one clock cycle. Now suppose CPU, the program counter floats an address to this bus so that the next instruction is to be brought in. Now please tell me what is going to happen here. We are at the first stage of the instruction cycle, instruction fetch. The program counter floats the address in this data bus. What is going to happen in the memory hierarchy? Where are you looking for? Where do you look for this instruction?
The instruction cache.
In the cache, right? Okay, so you compute the cache index from the memory address and then look into the cache. What are the outcomes? Suppose there is a cache miss. What happens next?
We stall the cycle until we can access it from memory.
You go to main memory. And suppose there is a page fault.
You have to go to the hard disk.
You have to go to hard disk, okay, and again, as you know, the hard disk is slow and so on, and you do the reverse process again. In the meantime, there are many stories behind it, right? There are dirty bits, write through, write back, and so on. So all this overhead has to be done. So as you can see, this instruction fetch, is not a simple story. Same thing will happen, when you are doing the data fetch in the memory cycle. For example, in the load instruction, you can have cache miss and then main memory miss, go to secondary memory and then do all kinds of associated overhead, isn't so? Page fault, then TLB management, then mismanagement, okay, the management of the cache miss, write back, write through, all kinds of things. all these procedures have to be completed in order to access the instruction or data. So I'm talking about single cycle processor design. Then what should be my clock cycle time?
The maximum possible time for an instruction to execute.
Okay, so this is almost infeasible, isn't so? So whenever there is, if you are lucky, okay, if you find anything, if you find the instruction or data in the cache, fine. You just find them in one shot. But if not, but you have to prepare yourself for the worst case as well, and therefore this is infeasible because you have to extend the clock cycle time, very long. So what are the other post solutions? Okay, so let us look into some logistics problem here. Suppose I have a sand pile here, and I need to move this sand pile from this position to another location nearby. And I have several workers, say a K number of them. Okay. So one possibility is that one worker approaches this pile, takes one bag here, and carries it to the destination and drops it here. Okay. The second person comes and he or she does the same thing. So that's one possibility, right? What are the other possibilities? Is there any other thing by which you can simplify or make this logistics a little bit improved?
So by forming a human chain.
You form a human chain. So let the first person come here and deliver to the next. So and you form a human chain. You pass it, to the next person and so on. So if you just do a simple arithmetic calculation, some basic calculation, you would see that the total work done in the second process would be much less, because you have to travel less. Okay, so this is an idea which is being implemented in this pipeline design and so on. So in the single cycle processor, as we have discussed so far, that everything has to be completed in one clock cycle. But now, since we have understood the complications of this memory access with so many miss and page fault and all kinds of things, so therefore, in case of single cycle processor, this time period, has to be take care of all worst case scenarios. It's almost impossible. Okay. So let us move into the other possibilities. So instead of having a single cycle processor, let us have. So we have these basic steps like instruction fetch, decode, register, execute, memory, write back. So let us first make our clock faster. That means the clock cycle time becomes smaller. And what we do that in each phase, each stage of the instruction cycle can be finished in one clock cycle, something like this. Okay. And then we would implement the concept of pipelining later on. First of all, we have seen that single cycle processor implementation is not feasible in a real life system because of memory access problem. So let us go into the multi-cycle case. So we have a short, now we need multiple cycles in order to finish this, but again we have this memory access, all kinds of problem, but we will install accordingly later on. Well, so now let us look into this again, how this concept of pipeline came into picture. So let me look into this picture once again, that your job is to manufacture a locomotive. Or suppose your objective is to manufacture some cars, cars or locomotive engines. So in the factory, what you are going to do? What is the naive approach? So I have labor and machinery to fabricate this, to build this kind of machinery. So everything I engage to finish one car and then proceed to produce the next. So you finish one car from the scratch to the end and then proceed to finish the next car and so on. That's the naive approach. So as we have seen in this human transportation chain case, what will be the better approach? Here. You must have heard about assembly line, right? So in assembly line, what you do? So you have different stations now, and in each station you perform certain specific tasks. And the chassis is moved from one station to another station. When it reaches the last station, it is finished there. So this is a very old concept, you know. And this is the basic idea behind pipelining. So instead of finishing one job at a time, just like in the single processor case, what we do it in multi-cycle or multiple stages, just like the car manufacturing. So chassis is moved through different stations or phases in sequence, comprising the relevant workforce. And in each station, you perform some specific task. And once the job is finished in this station, it leaves the station. It goes to the next station, and another chassis arrives in the previous station. So therefore, as you can see, that multiple stations are busy at any time instance. So subtasks are overlapped in time. And again, each station performs only one specific job every time. Just like you have the hardware which performs only instruction fetch, you have the hardware which performs register read and instruction decode and so on. So every step, it performs a specific action. But once the action is over, it passes this partially finished entity into the next stage, and then another entity arrives in the previous stage. Okay, but you need to certain precedents must be honored. You know. For example, so for example, in the 5-stage MIPS, you know, the instruction fetch should precede register read and decode and so on. So one after another in sequence. And these phases should preferably be balanced in time. You know. And we will see later why this is necessary. So as you can see, this concept of pipelining is very old. You know, it has been used in industrial pipelining in assembly line for a long time, and in computer architecture, this idea is borrowed. You know, this is very successfully deployed. Okay, so the idea is you divide into multiple phases, and you forward and conquer. And of course, you need multiple phases to need the complete production. And in each phase, you do some specific expertise, and you need some specific machinery or instruments or hardware, and you need some specific time to finish the execution of a particular phase. It is preferable that each phase should be finished in equal time. And you will see why that condition is necessary. So the ultimate objective is to optimize the total completion time for producing n cars, and in the context of computer architecture, we want to finish n instruction as early as possible. So you got the idea, right? And in order to implement this, obviously, you need this multi-cycle realization, because in each smaller cycle, you are performing one specific task. Do you follow me?
Yes, sir.
Yes, sir.
All right. So now tell me, what is in the pipeline? Okay, so let me start with a very simple example. It's a laundry room example. So maybe in your IIT hostel, there are some laundry room in which you have a washer, you have a dryer, and you have a place where you can iron your clothes. So there are 3 resources you need: washing, and then drying, and then folding or ironing. Suppose there are 4 students ABCD, and they have their load of clothes to be washed, dried, and ironed. And washing takes 30 minutes. Your dryer takes 40 minutes, and your folding takes, ironing takes 20 minutes. You have iron table and electric iron and so on. So these are the three resources and three substations, you might say, in my assembly line. One possibility is that, okay, this student A arrives, so he or she takes 30 minutes to wash, 40 minutes to dry, and 20 minutes to iron. So that means 90 minutes each. So once he or she finishes, so total 90 minutes you take for this purpose. So once the student A finishes, and then student B arrives, and he or she does the same thing. Again, it takes 90 minutes, and for student C another 90 minutes, and student D another 90 minutes. So 90 times 4, right? So how many hours it takes? It takes 6 hours to finish the job. So this is called sequential laundry. So you finish everything, and then the next user can enter. It's similar to single cycle instruction. You finish everything. Your instruction here has 3 steps. You finish everything in one step, in one cycle, and then only the next student gets a chance. So sequential laundry for 4 students would take 6 hours, right? So if you start at 6 p.m. in the evening, it would finish at midnight. Can you do better?
Yes, sir.
This is obvious, right? In real life, what you do, as soon as this washing is finished, right? As soon as the washing is finished and A moves to the dryer, the user B may start using the washer, right? And so on. So here, as you can see, that at any instant of time, so this is the time axis. At any instant of time, only if I draw a vertical line here, at any instant of time, only one resource is busy. Isn't it so? Okay, suppose you have this knowledge of pipelining, which is obvious. So here, for example, you can see that at this time instant, the dryer is busy, but washer is free. This is, I mean, because only user B is using this dryer, washer is now being idle. So there are many places. Similarly here, washer is idle. The idea behind pipelining is to utilize this idle time. So here, notice that in single cycle instruction, only one resource is busy at any instant of time. In the basic idea of pipelining, okay, so as you said, the user A arrives, so he or she takes 90 minutes. But then as soon as the washer is free, B starts his or her laundry here. And similarly, and this continues. Okay. So as you can calculate now, see, the first user takes 90 minutes and second user takes a total, how many, what will be, it takes 3.5 hours for finishing these 4 loads. That you can easily see. So what is the speed up? In the previous case, we required 6 hours. Here we need 3.5 hours. So there is a speed up of 1.7. So from this example, what do we learn? Okay, first of all, let me ask you a question. So if you look into the finish time of the first user, it finishes at 90 minutes here, right? And if we look at the finish time of the second user, what is the distance? What is the time difference between the consecutive finish times? Hmm?
40 minutes.
40 minutes. So there are 3 stages, correct? There are 3 stages. One is 30, one is 40, and another is 40. So you said
Another is the last one is 20.
that,
As the last stage is 20 minutes, as far as I remember.
last stage, yes, sorry, this is it. Yeah, last stage is 20 minutes. That's okay. You are right. But see, this takes 40 minutes because see, this guy is using the dryer.
Yeah, that's why.
Okay, so what you can see that, see this dryer, so this is 30, 40 and 20, right? Among the 3 time units, the dryer takes the longest one. Okay, so you can see this true that the interval for the dryer use must be non-overlapped in time. Isn't so? So therefore, the frontier is pushed by the amount which is the longest interval, isn't so? Because these 2 dryers must have must be non-overlapping in time. So this is very important observation, This is the way you are emitting or you are finishing the job is determined by the longest stage. And at any instant of time, say for example here, we said that for this particular example, we had the speed up of 1.7, right? Let me ask you the second question. What is the maximum speed up which is possible in this context? I mean, suppose there are ideal cases, Ideal cases means, here this pipeline is not balanced in the sense that you have 30 minutes and you have 40 minutes and 20 minutes. And because of this unbalance, it's difficult to achieve the best possible speed up. But can you tell me intuitively that what is the maximum speed up which is possible? In terms of number, 2, 3, 4.
It should be 2, like if we consider every step to be equal.
Okay, let me give you an example. Suppose you look into this time instant here. So here 3 resources are busy. So that means the 3 resources are being used in parallel at some instant of time.
Yeah.
So can't you infer that maximum speed up could have been 3 because 3 resources are being used in parallel. So if there are sufficient number of users or instructions, the maximum speed up would be determined by the total number of stages, because that's the maximum parallelism you can achieve. Do you follow me? Because multiple resources are overlapped in time. So the first question you have already answered, that what is the time difference between 2 consecutive finish times? So this is the time instant where the first user finishes, and this is the time where the second user finishes. So this difference, this time difference must be equal to the longest stage. Time needed by the longest stage, because these are the same resources and they must be non-overlapping in time. So time required to move an instruction 1 step forward is nothing but the longest time needed to perform a particular stage. And that's why it is 40. So it is the slowest stage which determines this time difference between consecutive finish times. And this determines that how the different instructions are getting finished one after another. So initially you have a latency of 90 minutes here, because 30, 40 plus 20. So this is the initial latency. After that, every user can finish his or her job in 40 minutes, in additional 40 minutes, isn't so? And that's how you calculate that total time is 3.5. So we have two observations here. One is the longest or the slowest pipe stage determines the consecutive finish times or the emission rate. And what will be the speed up when this number of users approaches infinity? We have three stages here. At most, three stages can be used in parallel. So therefore, you cannot have more speed up. You cannot have a speed up which is more than threefold in this particular example, because you have only three stages. So in this particular example, if n tends to infinity, you can calculate that it will become 2.25. It can never exceed 3. If all the pipelines are balanced, equal size, and there is no pipeline overhead, then it would achieve 3. Okay. So these are the two basic concepts in pipelining. I hope you have understood this. You have understood this, right? The time difference between two consecutive finish times, that will determine the emission rate or finishing rate of instructions, and what is the maximum speed up achievable. So therefore, in MIPS, as you can see, you have 5 stages. You can have at most a speed up of 5-fold, not more than that. If you have longer stage, if you have long pipelines, for example, in floating point and so on, you can have a much better speed up there. So the maximum speed up is limited by the number of pipe stages. So once you understand these two things, this answer to question 1 and question 2, you are done. Anybody has any doubt here? Here is the summary of the lessons. So it does not help the latency of a single task, because the first user would take the 90 minutes as before, but it helps have a significant amount of emission rate or finish rate. So therefore, the throughput of the entire workload is improved. That means if you are given in a program comprising of say 1,000 instructions, for each, if you look into every instruction, that it's not, there is no saving in time. But when you look at the 1,000 instruction collectively, because of the overlapping of stages, you have significant speed up. But mind that the speed up will be limited by the rate of emission will be determined by the slowest stage. And multiple tasks are operating simultaneously, and potential speed up can never exceed the number of pipe stages, because that is the most parallelism, that is the maximum parallelism you can achieve. And this is one of the reasons, why we try to have a balanced pipeline, because if the pipelines are balanced, then the speed up will be equal to the number of pipe stages. Unbalanced pipe stages reduce the speed up. For example, here, so you have 30, 40, and 20, and that's why the speed up reduces from 3 to 2 point something. And there is a concept which is called the latency. You need some time to fill the pipeline. Fill the pipeline means, see, if we look into this time axis, and if we look into this time period, let's see at 8 p.m. Here, all the 3 resources are busy. And also here, 3 resources are busy. You know. So here at 7 p.m. only 2 resources are busy. You know. And similarly here, at something here only 2 resources are busy. But there are some time instance or time intervals where all the 3 resources are busy. So when all the 3 resources are busy, you are getting the maximum benefit. You know. Okay. And that's when you get the maximum parallelism. Before that, you have some filling time and you have some draining time. You know. And also for each instruction, if you consider a particular user, he or she does not have any savings in time. But altogether, collectively, you have savings in time. Okay. And we'll talk about later that you need to stall for dependencies. Suppose now you have a cache miss. You know. So we need to do something else. You know. We need to stop our pipeline and wait to resolve that stop. So what you have learned so far, it's one thing to note is that single cycle implementation is infeasible, and pipelining is widely used in modern processors. It improves system performance in terms of throughput, but it does not reduce the latency. It does not speed up an individual instruction. It speeds up only the collective set of instructions. And it needs more complicated, more sophisticated compilation techniques and so on. The basic idea is you arrange the hardware so that more than one operation can be overlapped at the same time. And since we have multi-cycle implementation, we are talking about multi-cycle implementation, we would see that at some instant of time, maybe all stages are busy, like instruction fetch hardware, decode hardware, execute hardware, memory hardware, and write back hardware. All of them might be busy at the same time. So it increases the throughput, or indirectly it increases the average number of clock cycles per instruction, CPI. Right? It improves CPI value significantly because you can finish a number of instructions in a much lesser time. Well, but if a particular instruction is concerned, there is no savings. So if you look into this MIPS pipeline, we have all these 5 stages, and we have hardware for implementing each of these stages. We have just discussed that we have this hardware resources, but this is the design for a single cycle implementation. This will not work for pipeline. We need to do something else here. We need to augment this design in a certain fashion, in a certain way that we will discuss later. Well, let us look into a pipeline diagram. It's what we do. So suppose these are the instructions I want to execute. We have load, subtract, 2 R-type instructions, and these are all R-type instructions. And suppose I have a multi-cycle implementation. So in multi-cycle implementation, my clock cycle time is small. And in order to finish one instruction, I need 5 clock cycles. So in the first clock cycle, this if part is executed for the first instruction. In the second clock cycle, the instruction decode and register read is executed, and so on. So in the horizontal direction, we show this clock cycle time or the clock cycles. And in the vertical directions, we are showing the instruction. Now, one thing you can observe that, okay, so in order to finish the first instruction, I need this 5 clock cycle, right? Fetch, decode, execute, memory, write back. Now, if I do certain augmentation in my hardware, so as soon as the first instruction finishes this if part, this hardware becomes free, right? This hardware module becomes free. It can now process, in the second clock cycle, it can process the if part of the second instruction. Isn't so? I keep on doing this. So as you can see, if we look into the vertical direction, what do you see? If we look into in the vertical direction, if we look into a particular clock cycle in the vertical direction, what do you see? So these are all subtasks, right?
Yes, sir.
What peculiarities or what characteristics do you see here? If we look into any vertical axis,
It is like a complete instruction.
well, I mean, what I'm saying that I want to notice that there is no overlap of the same basic cycle. I mean, no component is repeated here. They are all distinct, isn't so?
Yes,
because
sir.
they have to be distinct, because you have hardware for each of them. So, I mean, you cannot have two write back or two execute in the same clock cycle. That's not possible. They must have to be distinct, right? Because one hardware module can perform task for only one instruction. And therefore, since my instruction is partitioned into different components and my hardware is also partitioned into different modules, so I have overlap in time, but these modules are all different. They are being active at the same instant of time. So this is the time where I'm getting maximum parallelism. And this is the time to, and here you can say that the pipeline is full now, because every module in my hardware system is now busy. See, this is the write back in clock cycle 5. See, the write back module of write back is performed for instruction 1. Memory module is busy in processing the second instruction. Execute module is busy in performing in processing the third instruction. And this ID instruction decode module is busy in processing the fourth instruction. And instruction fetch, this module is busy in processing the fifth instruction. So all modules are busy, but they are processing different instructions. Right? And therefore, this finish time, since the operations are overlapped in time, this finish, if you have 5 instructions, normally in single cycle cases, if I have disjoint cases, disjoint implementation, then for each instruction I need 5 cycles. Then for 5 of them, we should have required 5 into 5, 25 cycles. Right? But here I finished everything in 9 clock cycles. So therefore, the average number of clock cycles per instruction, or CPI, that reduces significantly. So this is called a pipeline diagram. This shows the execution of a series of instructions, sequence of instructions. So the basic idea is just like as soon as one hardware module becomes free, it can start processing the next instruction. Of course, things will not be so simple. There will be many more complications we would see later. And the instruction sequence, as you can see, is shown vertically, and the timing is shown horizontally from left to right. And each instruction, as we said, that it's divided into components, into 5 components, as in MIPS. And there are specific hardware modules for implementing each of these stages. and there are overlapping of instructions in a particular clock cycle. Here, for example, see there are in clock cycle 3, in the third clock cycle, see 3 modules are busy. Execute for the first instruction, ID for the second one, instruction fetch for the third one. So 3 instructions are being simultaneously executed by the system. part of theirs. So here 5 instructions are being, portions of 5 instructions are being executed simultaneously. So you can clearly see that this is the maximum amount of parallelism you can get here. Right? All the 5 components are busy, 5 modules are busy, and therefore the maximum speed up cannot exceed 5. This is trivial. All right. So any question here, or otherwise we may stop today and continue tomorrow. So there are 2 things we have observed. One is the maximum speed up, and other thing is that which determines this emission rate. The longest pipe stage determines the emission rate. All right. So any question regarding multi-cycle implementation or the basic concepts of pipeline speed up? The ideas are very simple there. Of course, during implementation, you will see there are many more complications will crop in, and we will see later on that how those can be resolved. You follow me?
Yes, sir.
Okay.
Yes, sir.
So, any questions or doubt?
No, sir.
All right. Okay. I don't know whether the recording has been done. Anyway. Okay. So let me stop here today, and tomorrow we'll see again. We'll resume again. We'll be having only classes for the next week, and then I think Professor RSC has already told about the last exam date. It would be held on 15th of November, I guess. All right. Thank you very much.